Hey guys, we were receiving multiple grievances about the sound quality of the STA series from multiple viewers over a long period of time. It took our serious attention. As a solution, we are republishing STA episodes by digitally remastering the audio. In this video, we are clubbing 4 theoretical Q&A episodes about LOCV, AOCV, POCV and clock gating as bonus. So stay tuned, stay focused. Hey guys, welcome to the 17th episode of Q&A. Viewer Swati Kulkarni has asked in the 5th episode of Static Timing Analysis series, Sir, can we do STA for gated clock circuit? I am not getting what to consider. She was designing a PUF circuit at her end. In the theoretical episodes of the STA in this channel, the clock gating topic was not covered. Hence, in this episode, we will go through the fundamentals of clock gating first and then immediately after provide the answer to Swati's question. Stay tuned till the end of this episode to know the basic know-how of clock gating concept in STA. Today's episode is split around in the below topics. What is clock gating? How clock gating impacts the circuit? How clock gating is implemented in the design? How does STA detect clock gating? What happens after the detection? And finally, we summarize everything. We are done with the menu. Let's move on to the topic. What is clock gating? Clock gating is a popular VLSI technique used in many synchronous circuits for reducing dynamic power dissipation. By using clock gating, the clock signal is removed when the clock is not in use. Cutting away the clock disables the portion of the circuitry so that the flip-flops in them do not have to switch states. So till these 3 points, it's a bit clear to you, right? That this clock gating is meant for power management. That means power saving. And where do we do the most of the power saving nowadays? Yes, it's the handheld devices like a mobile phone or a smartwatch or any other wearable devices. Will come shortly. Switch state consumes power. When not being switched, the switching power consumption goes to 0 and only the leakage currents are incurred. So this way we can optimize the power of any battery powered device. Thus, clock gating saves power by cutting away the clock tree at the cost of adding some more logic to a circuit. Now, when you try to optimize something, obviously some cost you have to pay. Here, it is nothing but adding a bit more circuitry into the main design. Clock gating works by taking the enable condition attached to the registers and uses them to gate clocks. This is one way. The design must contain these enable condition in order to use them and benefit from the clock gating. So shortly we will see there are some other ways of the clock gating too. But basically this is the main fundamental thing that happens in a clock gating. So all these bullets and the points and the informations in these bullets are very clear and straightforward. So without any further explanation, let's move on to the next slide. How clock gating impacts the circuit. Clock gating removes large number of multiplexers and replaces them with clock gating logic. This is what is done at the gate level, that is at the logic gate level by the clock gating methodology. Thus, clock gating process saves significant die area as well as power. Now you get the benefit. This clock gating logic is generally in the form of integrated clock gating cells, also known as ICG cells. These are part of the standard cell library. The clock gating logic will change the clock tree structure since the clock gating logic will sit in the clock tree. So thus, the clock gating impacts the entire circuit. We are done with this particular slide. Let's move on to the next slide. How clock gating is implemented in the design. Now this comes the real question. How it is implemented. Let's see. Coded into the register transfer level code as enable conditions that can automatically translate it into the clock gating logic by the synthesis tool. So this is one way that you can do it at the very beginning at the RTL code level and encode it in such a way that the clock gating logic is automatically implemented by the synthesis tool. That means where the Verilog or VHDL code is transferred into the actual gates, inserted into the design manually by the RTL designers, typically as the module level clock gating by instantiating library specific ICG cells to gate the clocks of specific modules or registers. Now, this is another way. First is the RTL modification, second using the ICG cells. Semi-automatically inserted into the RTL by automated clock gating tools. These tools either insert ICG cells into the RTL or add enable condition into the RTL code. This could be the third option where either the RTL modification or the ICG cell insertion can be judiciously done by the clock gating tool in an automated way. So the next point is tips used in the mobile devices, not only mobile devices, wearable devices also, such as mobile devices, that is mobile phones, wearable devices, etc. would implement several forms of clock gating combined together. So as we have the mobile devices, the battery power is very low and it has to sustain for a long time. Say you are using a smartwatch, it has to run long, at least half of the day, or best is the full of the day. So the power saving must be done, and that can be done with the judicious distribution of the multiple methods as discussed in this slide for the clock gating. However, there are several other power optimizations are there. I am not going to those because in today's episode we are focusing only on the clock gating. We are done with this particular slide. Let's move on. How does STA detects the clock gating? This is a very crucial question. You are thinking how the engine can grab the clock gating lock or the code or both from the design. Let us see. First, we have to trigger the clock gating check in the STA engine by using the command set clock gating check. First, we have to trigger clock gating check in the STA engine by the command set clock gating check, then dash setup, then asval, and then dash hold, and then asval. So this is the compact command. Now asval is the amount of setup time cushion needed. Asval is the amount of hold time cushion needed. If you don't know these two terms, I would request you to go through the STA playlist in this channel and find out the setup and hold analysis discussed in one of the episodes. The thumbnail speaks by itself, so you can find it out. Reading our input through this command, STA tool recognizes the latch in the clock gating circuit and assumes that this is a latch path. So now what we are going through, that how the tool detects this particular clock gating and what it does with after it finds it. So the STA tool further divides the path into two parts. Front path. This is the path in front of the latch. Back path. This is the path in the back of the latch. What happens after the detection? We come here very fast immediately after the last slide. This is the continuation of the last slide. STA algorithm will first analyze the front path. It will borrow time across the latch so that the front path can meet timing. Then it analyzes the back path given the amount of borrowing it did on the front path. Thus, it leaves the violations on the back path even though the front path appears to be meeting timing. Next, the tool recognizes that a failure in the back path can be improved by optimizing the front path. With STA, we have actual net delays, and so we can correct the time borrowing for each latch individually with high accuracy. To do so, we use set max time borrow command to allow the just enough time on the back path for glitch free operation while forcing all available slack to the front path. So these all things happen the post detection part, and this command at the last bullet we manually have to enter. We are done with this particular slide, so let's move on. Summary. STA does not have the analysis problem associated with the ideal clocks as long as the STA is run with detailed actual clock network analysis. Generally, when we reach up to the stage STA, you can find out. I have already displayed the flowchart in this particular static timing analysis series, first or second episode of this series. When the flow comes up to the STA, this actual clock network is ready. STA does incorrectly divide the clock path into two separate paths, thus obscuring potential critical paths. There could be critical paths where it does the algorithm for the clock gating. Some critical paths will get affected. However, for up-to-date algorithm and methodology, please consult your respective STA tools latest manual so that you do not miss out any up-to-date command or methodology that can cure the usual way of dealing with the clock gating paths. So folks, we are done with this particular slide. Let's move on. Hey guys, welcome to the 18th episode of Q&A. Viewer Mansoor Ali has asked in the third episode of Static Timing Analysis, what is POCV in STA? He is a fresher and hence looking for the fundamentals to understand POCV. In the theoretical episodes of STA in this channel, the statistical STA was not covered. Hence, in this episode, we will go through the fundamentals of statistical STA in dealing with the on-chip variation first, and then we will discuss its practical implementation as POCV. Stay tuned till the end of this episode to cover the basic know-how of parametric on-chip variation in statistical STA. Today in this episode, we will cover the below topics. First, we will discuss what is on-chip variation. Next, we will discuss the STA limitation, and from that point, the statistical STA begins. The statistical STA basic algorithm is the next thing that we are going to discuss. Then we will discuss what is POCV. Next, we will discuss the basic delay equation in POCV. We will understand how the POCV input files are different from the regular static timing analysis input files. And at the last, we will discuss the command that you need to invoke the POCV in the STA tool. So folks, this is the menu for today and let's begin. What is on-chip variation? Now before going any further, I would like to say that the POCV, the last P alphabet is OCV. So I have kept this slide, although similar slide was already there in the STA series. I have kept specifically here to reiterate the facts on OCV. Now what is on-chip variation? On-chip variation is a recognition of intrinsic variability of semiconductor processes and their impact on the factors such as logic timing. So this is a kind of dictionary definition of the on-chip variation. Next, PVT variation is inter-die, also known as global variation. We have already discussed about the PVT variation in the ST episode. Now why I kept this? Because there is a striking difference between the PVT variation versus the on-chip variation. Now, intra-die, that is single wafer variation, is termed as the OCV variation, also known as the local variation. The on-chip variation is intra-die, that is within a single wafer, and all about the spatial distribution of the variant. The OCV effect is predominant on longer physical paths in a chip. So there are start point and end point of very many timing paths which are very long in nature and going from one end to the another end of a single wafer. Although every chip size is much smaller than the whole wafer, however, in direction wise, this path can run from one end to another. So on those paths, the OCV effect is very much important. OCV variation impacted by temperature variation by 10 to 20 degrees centigrade. Hence, more OCV specific corners come into the picture than though typical first. I would like to mention here one thing. If you open up any standard cell library distribution, right, you will find typical, slow, fast, and there are many combinations of all these PVT corners. Now those are PVT corners. That is PVT variation, that is inter-die variation. But for OCV, generally we have a kind of format in the timing.lib that is called LVF. Come to that later words. However, this is much more important in sub-nanometer region chips, the OCV factor, and we proceed to the next bullet. The STA incorporate OCV effect by derating delays of the specific path. Both cell and net delay are subject to derating effect. So derating is nothing but a method of manipulation or to the existing delay with a particular mathematical expression. So that is derating, and that actually can replicate the POCV delays. There is no on-chip variation, that is the single wafer variation. POCV effect can be implemented in the STA tool using the following command: let timing derate early or late, whatever value you give, you can specify there. So folks, we are done with this particular slide. So let's move on to the next slide. STA limitations and statistical STA. Now, so far we have discussed about the STA. Inside that we have discussed the OCV, and at some point this gate a roadblock. Let us look into that particular area. Conventional STA cannot easily handle intra-die correlation, especially if the spatial correlation is included. I mentioned this word spatial distribution few slides back already. Now here you can see it. For intra-die variation, STA needs many corners to handle all possible cases. This is achieved at the cost of more standard cell characterization, time and resource budget that has an effect on the manpower who are generating the library, the standard cell library, the timing library, and all the dependent files and folders, whatever they are. Next. This motivated semiconductor research and development bodies to look for a more into a modern practical approach to perform static timing analysis. So this roadblock that for intra-die variation we have to create much more number of corners that will cause the standard cell characterization in a massive scale, and we get the corners after that, and then we do the STA for the intra-die variation. So this roadblock pushed all the research and development bodies in latest semiconductor industry to think for a much more modern approach. They borrowed the concept of statistics. That is, likely you are familiar with the word probability, standard deviation, etc. Yes, those comes from the statistics. They brought this statistics into the STA in a more realistic approach. Statistical STA replaces the regular STA timing of gates and interconnects, that is gates and nets, by the introduction of probability-based distribution. So here the statistics enters into the static timing analysis. Hence, the analysis report gives a set of all possible circuit output combination rather than a single situation. This is much more practical approach in sub-nanometer era. Now, when we have our conventional STA, we get the output, one single output for one particular path, about whatever we are looking for there. That is what we are considering right now. However, when we use the statistical STA, we get a statistical distribution, and the result is also containing the statistical result, which will contain much more possible output combination rather than a single particular situation. So this is much more acceptable, because when all the things are varying inside a single die, that is a single wafer, we do not know what is happening where, and better to consider all of them before our chip actually goes on to silicon and fails. The silicon failure is not at all welcome by any of the chip designing houses, because if the chip fails at silicon, they will have to face a huge market loss. So to stop that, in a sub-nanometer era, the statistical approach, the statistical way of analysis and the output interpretation and taking actions accordingly will help lesser number of silicon failures. So this is the significance where the boundary line of STA stops. On the other side of the boundary, the statistical STA starts acting. Folks, we are done with this particular slide. Let's move on. Statistical STA basic algorithms. This slide is kept for your basic know-how. When you are going through any particular tool manual, you might across come of one or both of the algorithms. That is why we are touch basing this slide. It's not mandatory to know. However, if you know this particular fundamental, it may help you in real-time work. There are two main categories of statistical STA algorithm, that is path-based and block-based. By the name, you can guess path means there is a path related and block means there is a design block. So let us see what are they. A path-based algorithm sums gate and wire delays on specific path. The statistical calculation is simple, but the path of interest must be identified prior to running the analysis. there is the potential that some other paths may be relevant but not analyzed. So path selection is very, very important. So here done with the path-based algorithm. Next point is the block-based algorithm. A block-based algorithm generates the arrival time and required time for each node and work forward and backward from the blocked elements. The advantage is completeness and there is no need of path selection. So these are algorithms that happens inside a tool, and the way the tool handles the mathematical computations and playing with the statistical rules there. So that's why all these algorithms are displayed to you, just to have an idea and a kind of virtual visualization what is happening inside your STA tool. The biggest challenge in the algorithm is that a statistical max or mean operation that is also considered. Correlation is needed, which is a hard technical problem. So folks, we are done with this particular slide, and I think a virtual impression of the algorithm has already printed in your mind. So let's move on to the next slide. What is POCV? Now, finally, we come to the slide of our concern of today's episode. POCV stands for Parametric On-Chip Variation, which uses a statistical approach. Up to this point, you have already known that we are dealing with the statistical STA, and POCV is somewhere in this picture. POCV handles the local random variation without requiring the statistical library characterization. POCV works based on statistical Gaussian distribution of cell or net delay instead of adding digit values. It calculates delay variation by modeling intrinsic cell or gate delay and parasitic R and C to determine both statistical mean and sigma variation. So far up to these points, you might have visualized that it is statistical STA. However, there is some plus thing onto it. So that is POCV, what we are discussing right now and what is displayed here. The cell delay is further broken down into N-channel components and P-channel components. You understand what are these two things. Then assume that all the cells along a path have the same mean and sigma. Next, in POCV, cell delay gets calculated from either library or POCV table. We'll come to this. Since POCV is statistics based, it can't slide into just any STA tool. Rather, it needs a statistical STA engine in order to be used. What we mean by that? That all the statistical mathematics have to be enabled in the engine, and that engine is not same as that our conventional STA. We know it theoretically it is different. The statistics mathematics related to it is very much different than our regular mathematics. So this engine must have all the statistical necessary mathematics and algorithms enabled so that the POCV can run onto it. So here comes the plus factor that I was talking about the POCV. Next, we are discussing the basic delay equation in POCV. Why we need this thing, the basic delay equation? It is again, the tool is doing its calculation. You don't have to bother. However, you need a virtual visualization of what is happening inside. That is the necessary of this equation. Right now, it is getting displayed to you. The new cell delay after the POCV can be defined as delay new is equal to delay original plus delay variable into param. So what are all these things? Delay original is the original delay of the cell without applying any derate. Next, delay var is one standard deviation value of the delay distribution of the cell. Param is the standard random variable, that is n. So these are all statistical terms. So this way you can visualize the new delay that has been defined inside POCV engine. We are done with this particular slide in a short and sweet manner. Let's move on to the next one. POCV specific input files. So this is the thing that I was mentioning that few slides ago. We will talk about how the input files are different. Mostly the POCV specific files we are talking about here. Rest of the files, whatever we have discussed for STA, they will be there. However, we need some additional files, and these additional files can be provided to the POCV engine in two ways. The first way is POCV liberty variation file. So I just talked about few slides back about this also. It is also called POCV LVF, which is I think comes in the timing library. And the second way is we combine two type of files together. The first one is POCV distance delete files, And next one is the POCV coefficient file. So we have two different approach of giving the POCV input files. One is the LVF file, which is on your left side, and on the right hand side there is a combination of distance relate file and coefficient file, which have to be provided together to the POCV engine. So once you deal with the tool, you will come across these files. So in a short and sweet manner, this slide is already discussed. Let's move on to the next slide. POCV STA command. You might be wondering up to this point, so far we have discussed all the theories and everything. However, when we want to invoke the POCV inside our statistical STA tool, what command we should use? So the command is variation_analysis. It is the command that is the tickle proc, and the arguments are mode. We give the value as POCV, then we give from and to, that is the path starting point to the path end point. And then we mention about the delay type, that is max for data analysis or mean for hold analysis. So this is in a short and sweet manner the command to invoke the POCV. Anything happening statistically, it will be taken care by this particular tickle command. One thing I would like to mention here. Always check your latest tool command manual for the command, because the VLSI industry is always changing, even every day, every minute, every second. So whenever you are trying to use any command, check its latest manual. So there might be some changes or updation. You must adhere to these changes or updation to get the full output from that particular command. So with that, I'll conclude this slide. Let's move on to the next slide. Hey guys, welcome to the 19th episode of Q&A. Viewer Rajshri has asked in the 18th episode of Q&A from Static Timing Analysis series, what is the difference between AOCV and POCV in STA? In last episode, we have discussed about the OCV and parametric OCV, that is POCV. However, AOCV was not covered. Hence, in this episode, we will go through the fundamentals of advanced on-chip variation, that is AOCV in STA. If you watch the last episode and this episode back to back, then you will be able to differentiate OCV, AOCV and POCV. Stay tuned till the end of this episode to cover basic know-how of the AOCV in STA. In today's episode, we will be discussing about what is AOCV, which is also known by another name LOCV, working principle of AOCV or AOCV, understanding the LOCV or AOCV derating table, timing dotted data format or AOCV or LOCV, the analysis types of LOCV or AOCV. So that's the main for today. Without any further ado, let's begin. What is AOCV or AOCV? So this AOCV is implemented for intraday, that is single wafer timing variability analysis. This point is very much same as the OCV. However, it is less pessimistic than the traditional OCV, which has a fixed derating value. Means that the derating is a kind of constant everywhere for every gate, and it do not have any kind of distance or path relationship. It's just a static number. So in actual practice, when there is a wafer and the process to which the semiconductor chip is made, all those variations, the process variations happens various parts of a single wafer itself. If we traverse from one end to the another end of a single wafer, there may be difference. The difference can be found even for a single process step. So how can the effect be same or very pessimistic? However, these AOCV things became very prominent around the 65 nanometer node or below. Above 90 nanometer node, there was no need to see about a AOCV or LOCV. But in the sub-nanometer domain, when we went down around or below the 65 nanometer node, that time this AOCV has a great importance. Derating is a function of path or graph in AOCV or LOCV. So as I just mentioned that if I go from one end to the another end of a single wafer, how we move on top of the wafer, definitely there will be a path. And the graph is another concept in VLSI, especially in timing. So derating here in AOCV is a function that is dependent on path or graph. Hence, the name is appropriate, location-based OCV. Why it is important? Because this location-based OCV, the locations are determined by the path. Hence, the name is much appropriate, the location-based OCV. Or the more popular name of it attached to it is Advanced OCV, that is AOCV. In the industry, the less common name is LOCV and the more common name is AOCV. So, we are going to mostly call by the name Advanced OCV or AOCV. This is a non-statistical method as compared to the parametric OCV, that is AOCV. With AOCV already we have discussed in the last episode of Q&A, and that was a statistical method. However, this is not a statistical method. It is an advanced version of the Ponzi variation where we take the consideration of the derating variation depending upon the path in traversing one end of the wafer with another end of the wafer of the single chip. However, in these paths, there will be logic gates. We are not moving randomly. We are done with this particular slide, so let's move on. Working principle of LOCV or AOCV. In this method, the cell or gate derate varies with logic depth, that is hierarchy, and based on the path or graph. Logic depth, you understand that the gates are connected or the blocks are connected and we go inside a block, we have a sub block. This way we have the logic depth or the hierarchy. This path may extend from one end to the other end of the same chip, that is the wafer. Already I have a couple of times mentioned this thing. Such path may not consist only a single type of gate, rather various gates. Obviously, the design will contain multiple types of gates inside the silicon wafer. In this path, equal and opposite kind of derating may partially or fully neutralize each other's effect. This is theoretical. In practical, you can see it may happen, it may not happen. There is all type of possibility. Derating values varies for each cell type, each depth, each location, each slew, and each load. You can understand the derating values are also dependent upon various factors as cell type, depth, location, slew, and load. Using standard cell characterization to get the minute or accurate data, AOCV or AOCV requires a lot of library characterization manpower and hardware or software computational resources as compared to each ancestor. It is OCV. And this is a very much important point because we perform the static timing analysis. We have a very much needed input, the timing.lib, which comes to the standard cell characterization. Now, for this LOCV or AOCV, we require a huge amount of manpower and hardware or software resources. Manpower in the term that more man days rather than more people counts more man days, that is work weeks, are spent here on standard cell characterization. This is one fact about the AOCV in the background, not in the STA tool, but in the background requirement I, that is timing.lib. Worst case derating is picked up across each load or slew pair combination. So this is the part of the method. We have load slew pair, you know, from the timing.lib, right? So there we have the load slew pair and we have a LUT, and from there we pick the data. In case you have not watched the timing.lib episode in the STA series, go ahead. You can find it in the STA playlist and from there you can watch it. So folks, let's move on to the next slide. Understanding AOCV or AOCV derating table. As I mentioned that the AOCV or LOCV is a path or graph dependent entity. So the derating is not fixed here. It varies. How it varies, that is we are going to determine or see here. Here is a kind of representation of the silicon wafer. It's a hand drawing. So Here the oval represents a silicon wafer and the arrow is a path where we have the logic gates in the path, and the numbers there you can see 0, 1, 2, 3, etc. give the logic gate. And how we have the derating table, this picture will help you to understand. Here goes our derating table. First we have indexes as date, that is 0, 1, 2, 3. Then we have indexes as 200, 300. The units can be found at the top of the .lib file. I have mentioned in the timing.lib file. We have already explained what is there in the header section. These basic units can be found in the header section. Next comes the table. So you can see there are 1, 2, 3, 4. 4 columns and 2 rows. These 1, 2, 3, 4. So this goes for the columns and these 2 goes for the rows. Thus we create a hidden table to get the corresponding derating. So thus the derating can vary. This is the AOCV table. I have just give you a kind of snapshot on the actual table. I will show you the actual table later on, just for your understanding, just to create the right impression to your mind. This slide is created. Just take a snapshot in the mind. Yes, in upcoming slides we are going to discuss about the actual table. This is the actual data, but the table consists of much more data, but this is the crux of the table where we have the variation of the derating. We're done with this particular slide. Let's move on. Timing.lib data for POCV or LOCV. So here we are going to come across the actual table. So first there will be a header section of the table where these things are mentioned. The library, OCV lib, then OCV table template, would be OCV template. This is the name. Then variable 1 is path date. Variable 2 is path distance. Now you can see that we have named it. This is a table prototype. It is declared in the top section of the .lib. And we have dummy indexes 1 and 2. In actual case, these indexes, values and numbers can vary. On here we close it. So this is a template, that is the prototype of the actual table that we find later on inside each cell of the .lib file. Now what we see in the actual cell, inside is every cell definition. Let's look into that. And here the bigger rectangular box will be displaying that. The first we default OCV derate group, that is advanced OCV. Next we have the cell name. Then we have OCV arc depth 2.0. So this OCV arc depth is the effective logic date that is seen or a timing mark. We have a value here. OCV derate group AOCV 1. Then we have OCV derate, where it begins. OCV derate factors is OCV template. On RF type, it is rise fall type, and here in this particular cell it is rise and fall. However, the valid inputs can be in the right hand side as comments, right? The valid are rise, fall and rise and fall. So these are the types. Next, the derate type is early. This is the type of the arrival time. So it could be early, it could be late. These two values can come together. Next, the path type. So here the path type is clock and data, and the valid types are clock, data and clock and data. Now here comes the actual indexes. Next, we have the second index. So here you can see from the prototype, the index number and the values have been changed. Next, we have the values. That is the table, actual 2D table, lookup table. So here the table closes. So already you can now correlate. In the previous slide, we have discussed these two things and this thing. We have visualized in actual the timing lib. This is written in this way. First, this template is defined somewhere up in the .lib, and later for each cell, this section comes for the AOCV, and the relevant strings I have kept here. So this is a short and sweet description of the data that can be found in the timing.lib that has to be characterized by the standard cell characterization scheme, and this particular data requires a lot of effort. There could be various variations for a single cell. So every possible combination has to be logged there inside the .lib. So I have just given you one snapshot. And if you see right here, the values rise, fall, rise and fall. I am moving my mouse, so clock data and clock and data. So all these combinations, multiple combination of these variables can be there. Next, analysis types of AOCV or POCV. There are two basic types of the AOCV or POCV. In this slide, we will also see the snippet of the commands that are going to use. So first, see we enable the AOCV, we use this particular command in the STA tool, timing AOCV enable analysis in the values true. And this invokes the AOCV engine to read the respective AOCV inputs and process the design accordingly. Now, the first type is graph-based. As we mentioned, to initiate this particular method, we use report AOCV in this particular command. The first command already invoked that enables AOCV, and the second one invokes the graph-based method. The second method is path-based method, which is invoked by the report timing and then -EDA mode path. With this way, you can invoke the AOCV method inside the STA tool. Obviously, there will be a lot of other commands, but these are the key commands that we put here. So folks, in a short and sweet manner, we have covered this particular slide. Let's move on. Hey guys, welcome to the 22nd episode of Q&A. Viewer Subhash has asked in the episode of SDF file from the Static Timing Analysis series, what is pulse rejection limit and E-limit? Today, we will be focusing on the definition and example of both the pulse rejection limit and E-limit. So sit tight and enjoy the learning experience. In today's episode, we will be covering the below topics: SDF delay, SDF path pulse, the pulse rejection limit, that is also called R-limit, and in the same particular path pulse, we also have the X-limit, or which is also called E-limit. And we will see the various case studies for the above two. So that's the menu for today. So without any further delay, let's begin. SDF path pulse, pulse rejection limit, also called the R-limit. The path pulse entry represents narrow pulse propagation limit associated with a legal path placed between an input port and an output port of a particular device. These limits determine whether a pulse of certain width can pass through the device and appear at the output. Here is the example. I have shown you this example in the main episode, that is episode 9 in the Static Timing Analysis series. In case you have not seen that particular episode, please go ahead and watch that episode. So here we complete the example, and here is the infographics for the pulse rejection limit. So here in the picture, you can see that two limits have been defined. Now here, if we compare this particular picture with the values, the first value 13 is in time units, is the pulse rejection limit, also known as R limit. This limit defines the narrowest pulse that can appear at the output port of the specified path. Any narrower pulse does not appear at the output. So you can understand from the picture and the example that if pulse width is less than 13, then it is rejected. That is, this is the pulse rejection limit, and we can set it in the SDF file. So I think this is a very clear and present fact. We are done with this particular slide. So let's move on. Now let us look into the X limit or E limit using the same particular example. And here goes our infographics. The second value 21 in time units is the X limit, also known as the E limit. This limit defines the minimum pulse width necessary to drive the output of the specified path to a known state. A narrower pulse causes the output to enter into the unknown state or is rejected if smaller than the pulse rejection limit. Note that the X limit, also known as E limit, must be greater than the pulse rejection limit to carry any significance. So here you can see 21 is greater than 13, which is a very much clear and present fact. This kind of numerical difference should be there when these two limits are set. If you specify only one value, both limits are set to that particular value. That means instead of 13 and 21, if we have used only 13, so that particular 13 would be applicable to both the pulse rejection limit as well as the E limit. So that's all the explanation here. Next point, in all cases, value can be either a single number or a triple, but must not be negative. So this word of caution you must remember in your mind. Now we will look into various case studies. We'll use the same example and we will use this particular infographics here. In the first pulse, being shorter than 13, it is rejected. The second pulse, being at least 13 but shorter than 21, appears in the output as X. The third pulse, that being at least 21, is passed to the output. You can see that bullets and the infographics are side by side. So this way, this particular limits, that is pulse rejection limit and the E limit. Also, I have given the other aliases to you. This actually defines the transmission of a pulse from an input port to an output port. So here, we are done with this particular slide. Let's move on. Thank you very much for watching up to this point. And don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below. And bye for today.